So, how did the recorded lecture go? Y'all have any questions? The first lecture was on transducers. Unfortunately, the book splits transducers into two chapters. So the chapters that the lecture came out was chapter 8, and then chapter 15, which is our photoelectric transducers. So what is a transducer? What's another name for a transducer? Church what? Sorta. Energy, you're saying changing energy to energy. Huh? Well, you're saying energy to energy. Yeah, but it's still energy to energy. I mean, so you're saying what type of energy? We got all types of energy out there. You can't say it without defining. So what does a transducer do, or a sensor? Of course, the other name for it is sensors. And in automated manufacturing, these are just as important as your sensors. So what sensors do you have? Smell. Smell. Okay, so that's our sensors, and what does our sensors do? So when I come up here and touch something, what does it do? Yeah, it converts a physical quantity. That's what a sensor does. So it's not converting energy, it's taking a physical quantity and converting it over to its electrical equivalent. That's what a sensor does. Everybody understand that? So that's exactly what a electrical sensor does, or a transducer does. It takes these physical quantities like pressure, smell, scent, sight, and all that other kind of stuff that just like we have, and converts it over to an electrical pulse or an electrical equivalent, so your brain can process it. So your brain does not process touch. Your brain does not process smell. Your brain does not process hearing. It processes an electrical signal that represents that, right? You understand that? Everybody understand that? So when I come in, these sound waves come into my ears, it comes into my eardrums, my eardrum vibrates, it creates an electrical signal that goes up to my brain, into the section of my brain that takes care of hearing, and now I can hear. Okay, everybody understand that? So in automated manufacturing means we manufacture something with little or no human intercession, then or intervention. Then what does that mean? Well, we're going to definitely depend on sensors, right? You understand that? So chapter 8 and chapter 15 deals with sensors. And what some of the sensors they talked about. Of course, we talked about this. I don't know what's going on here, guys. Let me these are the ones that chapter 8 talks about. They talked about thermistors, photoresistors. Well, photoresistors is actually chapter 15. Hall effects, ultrasonic, piezoelectric. And also talked about different gas sensors. I think that was covered in. So what does a thermistor do? So what does a thermistor do, guys? So most of y'all did, when we did our questions on this chapter, just about everybody did a question on thermistors. So it's kind of hard for me to understand how you could come up with a question on thermistors and you don't even know what a thermistor does. So what does a thermistor do? Well, it's not a regular resistor, because if it was a regular resistor, it wouldn't sense, huh? Hey, yeah, that's what it does. Thermistor, thermal resistor, thermistor. So what does this guy do? varies its resistance, but you don't touch it. I mean, it varies its resistance with what? With heat. That's what it does. Thermistor. I mean, that guy right there is just about in the name. It tells you what it does. So you can see what they've done is just shorten it down, but it's a thermal resistor. And of course, they shortened that down years ago to what we call a thermistor. And we have two types. We have what we call an NTC and a PTC. What's the difference between an NTC and a PTC? Yeah, but that's what it stands for, but what is it? I mean, so yeah, right. So PTC is a positive temperature coefficient and NTC is a negative temperature coefficient. So what does that mean? So it varies its resistance in heat. Positive temperature coefficient. What would you think that means about the resistance? Does it go up or does it go down with heat? Positive temperature coefficient. So what do you think the resistance does? Does it go up or does it go down? Goes up. Yeah, positive temperature. Positive, okay. A negative, an NTC is a negative temperature coefficient. What would you think that guy would do? The resistance would go down with temperature. So it pretty much well falls into line. These guys here are not hard to understand, but they're all over the place. Now, they're not extremely accurate and they're not linear, but most of the time it doesn't really make any difference because most of the time the temperature is not that critical, right? You understand? I wouldn't use a thermistor in my oven because when you bake, it's pretty critical, right? You understand? And you need to bake over a pretty wide range. But as far as varying the temperature in a house, the temperature is such a narrow range that we run our houses at that, by the way, they don't have air conditioning in Germany. They just open, they have heat. So what do they do? It's they're even in the summertime, they don't get much over 70 degrees in the summertime, so they usually just do what? Open windows. I had a friend of mine that lived in Maine here. He said, we don't have air conditioning. So we use these, not extremely accurate. Photoresistors, we'll look at this. Hall effect. What does Hall effect do? What do Hall effect sensors do? Huh? So let's look. What does the Hall effect sensor do? So these are a little different. These guys right here are just resistors. Hall effects, these are electronic circuits. So right off the bat, as soon as I say electronics, it means we got to power these puppies up. These guys have got to have power applied to them. Okay, and it's going to be a DC quantity we're going to put on here. Everybody okay? And then we're going to have a next wire that's going to be what we call the signal wire. So these guys are going to have at least 3 pins on them. They're electronic circuits. They're going to have at least 3 wires or 3 connection points to them. 2 for what? Yeah, 2 for power, and then 1 for the what? Signal. So the signal is what it measures. So what does it measure? You're good. So this guy here measures a magnetic field. And we have different types. Unfortunately, I don't have the actual analog type. So what's the difference? We have 2 things the sensor is going to give us. It's either going to be a digital sensor or it's going to be an analog sensor. So what's the difference between a digital sensor and an analog sensor? What is digital? Basically, when we deal with digital sensors, these guys will only have 2 states. We call them off and on. We call them 0, 1. We call them true, false. So if this was a digital sensor, that means when a magnetic field came in contact, it's either going to give me a voltage or it's going to give me a ground, depending on what type of sensor it is. An analog sensor would actually give me a voltage that represents the strength of the field. Now, the one that I have is what we call, it's a digital sensor, but it's what we call a latching sensor. So this is my, oops, wrong camera, guys. Let me see if it'll let me bring up my other camera. I doubt it will. They don't like using two cameras at the same time. Yep. Hold on a second. This one right here would be too hard for me to hold, but it picks up infrared, so so we have a light emitting diode. Everybody okay with LEDs? It's actually in the next chapter, but it's in this section right here. So this is the Hall effect sensor right here, this little thing right here. And then if I look at it, it's got 3 leads, 1, 2, 3. Then we could look up the data sheet, and it would tell us which one is power. So on this one, this guy right here is power. So I have 9 volts coming in on this wire right here. The black wire is ground, and then this pin out here, pin 3, this is the output. And I have the output hooked up to a light emitting diode. And so notice right now it's turned off. And this resistor here, this is a 330 ohm resistor, and it's in here to protect the LED. So this is a magnet. And all I'm going to do is I'm going to come up here, and can you see what happens? So this is what we call a latching Hall effect sensor. Right now this is latched. And what's it waiting on? It's waiting on the opposite magnetic field. So one field turns it on. See, so that field turns it on. I'd have to look it up. And then this field right here does what? Turn it off. But all I'm doing is switching that is I'm switching it with a what? With a magnet. That's all it does. So a Hall effect sensor senses a magnetic field, but it's an electronic circuit, which means it's got to have what? It's got to be powered. So normally these guys have at least 3 leads coming in. Sometimes they have 4. Common is 3. We have a power pin, then we have a common pin, and then we have a what? A signal pin. And this is a latching. I don't have any analog. I need to order some. So if it was an analog sensor, what would happen is I would put a voltmeter across the sensor, and the closer I got the magnetic to it, the voltage would go up. The further it's away, the voltage would go down. So we use these things to measure. These guys here takes a certain number of flux density, I forgot what they call that, to switch on or switch off. But one magnetic field will do what? Oops, wrong way, Rich. One turns it on. How long will it stay on? Well, it'll stay on as long as power is applied. And then the other field does what? Turns it off. So this is a Hall effect sensor. This is a thermistor circuit. There's no power on it right now. And this is a Wheatstone bridge. Y'all understand Wheatstone bridges? So what do we use Wheatstone bridges for? Yeah, well, what we have, and this is what I showed you on the lecture. By the way, I'll put the lectures back up there now. So what we have is a series parallel circuit, but it's not a very complicated series parallel circuit. And what we do, we'll put a voltage across this thing. Now, if all these resistors are the same size, it don't make any difference what they are. Now, these are all 20K ohms. I'm not going to put the ohms. And so what would happen is that, and what I'm doing, we could use either other side. It's I'm going to put right now I'll put a voltmeter right here. Now, with 20K, 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 I could come over and calculate this, and we could use the voltage divider formula. So if I call this R1, I call this R2, I'll call this R3, and I call this R4, and we'll calculate the voltage drop across R2 because both these are going to be the same. So the voltage divider formula said VR2 would be equal to the size of the resistor divided by the total resistance. And of course, K cancels, the 0 would cancel. So that's 2/4, which means this resistor right here would drop exactly 1/2 the voltage. Of course, we knew that because it's a series circuit, right? You understand. And if the resistors and all the voltage in a series circuit has to drop the applied voltage, right? You understand that. So the voltage, the individual voltage drops in a series circuit have to drop the applied voltage. Two resistors, if they're the same size, they drop the same voltage. So how can I drop the entire voltage? Well, this guy right here's got to be dropping 2.5. This guy right here's got to be dropping 2.5, right? So right now I'd have plus 2.5 volts right there. I would have plus 2.5 volts right there. So what would my meter read? What would that voltmeter read? Huh? So what's the difference? So a meter measures a difference in potential. So a difference in potential, so that means I have a plus 2.5 on this side minus a plus 2.5 on that side. What's the difference in potential? It's 0. So we say the bridge is balanced. The bridge is balanced. So if the bridge is balanced, it means the ratio of this side and the ratio of that side are equal to each other. So over here I could put 5K and 5K, I could put 2K and I could put 2K, but the ratio of the resistors is 1/2, right? So any combination of resistors that comes up with 1/2, then the bridge would be balanced. And the voltage drop between this point A and point B would be what? Would be 0. Now the problem is that when I set a temperature, a thermistor changes its resistance with temperature. But when I look at a temperature, I talk about 32 degrees, I talk about 15 degrees. That's not just a resistance, that is a value, right? You understand? So what do I need to do? Well, I need to set up what we call a reference, an origin. I need to set up what 0 is equal to. And of course, the centigrade scale is a lot easier to work with because we have 0 is equal to what? Freezing. And what's boiling in the centigrade scale? 100. course, over here in the good old USA, what do we use? Yeah, and what's freezing in the Fahrenheit scale? 32. And what's boiling in the Fahrenheit scale? 212. So between degrees, we have 12 increments in the Fahrenheit scale. Between each degrees, we have 10 increments in the centigrade scale. So which one makes more sense? So they were laughing at us over there about the way we make measurements over there. Because centigrade in the metric system moves in tens, right? So we're over here still dealing with what we call the imperial standard or the English standard, when the rest of the world is dealing with what? Yeah, the metric. So bye, George. We're not going to change, are we? So let's talk about the centigrade scale. So what I could do, so if I came over here and change this right here, so I can change these resistors to whatever I want to. So let's leave that 20K over here, and let's make this a 10K right there. And I'll come up here. And I'll make this a 2K, and down here I'll make this a 1K. What's the voltage drop going to be? Well, if I calculate the ratio over here, that means DR2, which is our reference resistor, would be equal to 10K divided by 30K. Y'all understand the voltage divider formula. So what do? You take the resistor you want the voltage drop across, you divide it by the total resistance of the circuit. So this is K, this is K. Okay, then I would multiply it times the applied voltage. The K is going to cancel, this is going to cancel, so that means this is going to drop 1/3 of 5 volts. So what would that voltage be? What's that? 1.67 or 1.7 volts is close enough. So 1.7 volts over here. Now over here I have what? Over here I have VR4, which is our reference resistor, would be equal to, because it's the one that's referenced to common, right? You'll understand that. So that's why we use this resistor at the bottom. Would be equal to 1K divided by 3K, and the K's cancel, times 5 volts. Well, this is going to be equal to 1.7 volts. So that would be 1.7 volts right there. That'd be 1.7 volts right there. What would the meter measure? 0, because the bridge is balanced. So what I'm trying to show y'all is if the ratio of these two resistors match the ratio of those two resistors, then the bridge is balanced. And between point A and point B, we would measure 0 volts. Now, the circuit I have set up over here, so just about any, I'm not going to say always, so normally if we got a resistor, we got 3 units we can represent, or 3 electrical units we can represent something. What's the 3 units we can represent, these sensors can represent something in? They got to either represent it with a what? It's got to represent it electrically, guys. We've only got 3 units in electricity, right? You understand? What's the 3 units? Volts, ohms, and resistance. Now, watts is power. We're talking about electricity, right? So watts is the rate of doing work. So that means my sensors are either going to have to give me a voltage, they're going to have to give me a current, or they're going to change their resistance. Now, which one do you think is the most popular? Yeah, voltage. Good gracious, voltage is real easy to do. So let's say I came over here and I had a thermistor and I wanted to get an output from it. Well, if I came over here and I used nothing but a simple thermistor, and this right here was plus 12 volts, what would I always get across the thermistor? It's the only element in the circuit. It's going to always be what? Plus 12 volts. Now, I could use current, but current is hard to use, right? You understand that? So what does that mean? Well, that means, by George, if I'm going to use a thermistor, I'm going to put a fixed resistor in series with the thermistor. Now, I can put the thermistor at the top, or I can put the thermistor at the bottom. Now, if I come over and take that voltage measurement right there, and it's a NTC thermistor, that means as the temperature goes up, the voltage drop across the thermistor is going to go down, and the voltage drop across the fixed resistor is going to go up, right? You understand? So if the voltage drop, if the resistance goes down, then total resistance goes down, total current goes up, which means this fixed resistor is going to drop more voltage. But now I've got a voltage that represents the temperature. But I still can't set zero. Okay, y'all understand that? So what would happen if I put my thermistor right here, and over here I turn this into a pot wired as a rheostat? Well, what I could do is I could take my thermistor and I could put it into a glass of ice water, and then I could adjust this until my meter measured what? Zero. Now I've got a reference for that right there. Y'all understand that? So now when the voltage changes, I've got a reference to a temperature. It would be easy for a computer or something to convert that over to a temperature, right? So now we would have so many volts per degree. So we use Wheatstone bridges. So just about any device, if I'm gonna have to set an origin, or if I'm gonna have to set a zero on this resistance, on these sensors that change their resistance with temperature, I'm going to use a Wheatstone bridge, or they're going to use a Wheatstone bridge. And we've got all types of transducers that change their resistance relative to what they measure. But we got to start off with an origin. So we use devices in scales. They're called strain gauges. They vary their resistance with weight. Well, by George, I want to know what zero weight is equal to, right? So how do they set zero? Well, they set zero with a Wheatstone bridge. Now, once I've set zero in a Wheatstone bridge, now and we get a voltage out of them, right? You understand, because we put that fixed zero in there. Now I get a voltage that represents weight. And now my scale can take that volts, right, you understand, and interpret it as what? As a weight. We can take what we call a DAC, an ADC. Anybody know what an ADC is? This is an analog to digital converter. So what's in your meter? Your meter's digital. It's measuring analog quantities. So those voltages and everything's got to mean something, right? You understand? Does that make sense? Of course, here we're pretty lucky in that zero is zero. But if I pop the meter on, odds are I'm going to see a resistor. That resistor is going to allow us to calibrate or take out for some stuff that we don't realize is going on. And it's going to come into a Wheatstone bridge. And it allows me to set a watt. It allows me to establish what zero is or what origin is. So all these robots over there sitting there, they have sensors out there that sense their position. But those sensors, when I install those sensors, they could go in there anyway. So what do I have to have the ability to do? I have to have the ability to set what the origin of the robot is. Of course, we don't do that with a Wheatstone bridge, but it's basically the same technique. So we got batteries in that thing. So Wheatstone bridges. So usually any sensor, if we're going to establish an origin or a zero on that sensor that changes its resistance with whatever it measures, then we're going to use the Wheatstone bridge. So these guys are very, very popular. You're going to run into them quite often. So what is the note? So Hall effect measures what? Magnetic field. It's an electronic circuit, so it's going to have to what? It's going to have to be powered. What is an ultrasonic? An ultrasonic is an electronic sensor. So it's going to have to be what? Powered. Right now, we don't need to know how it works. We're just looking at what it does. So what does an ultrasonic sensor do? What does it measure? What does an ultrasonic sensor do? It uses sound to measure what it's measuring. So it don't measure sound. So my wife's got these ultrasonic sensors on the back of her van that when she's backing up, it goes indicates she's fixing to run into something. She's got mirrors out here that when somebody's up beside us, they come on saying, okay, there's somebody beside you. It's got ultrasonic sensors out there. So what does ultrasonic sensors do? They use sound to measure what they measure. They don't measure sound. Well, that's not true. They measure reflected sound. So what do they measure? Hey, these guys here measure distance. That's their function in life, is to measure distance. They measure, they send out a sound pulse, and they calculate the amount of time it takes to bounce back, which is proportional to distance. We have analog here, we have digital here. By the way, ultrasonic sensors are analog, but we run them into a what? An analog to digital converter. So this Hall effect sensor has an analog to digital converter built into it. That's part of the electronic circuit that's in there. The ultrasonic sensor that we have over on the Amatrol line is a digital sensor. It's an analog sensor, but it's got A to D in there. And what we have the ability to do on that is set a span. A span is a difference between 2 points. So what we can do is we can say, okay, if that unit is in between this level, it's good. If it's not between that level, it's what? It's bad. We call that the span, a span. So a span is the distance between 2 levels, right? So what does piezoelectric do for us? Anybody smoking here? Nobody smokes? Y'all probably use, if you've ever used the lighters in the old days when you bought a good old Zippo, how did you light those things? Well, it had a flint on it. I've got one, by the way. I got a Zippo lighter at the house. And what you did is you spun it, had a flint, which created sparks and lit it up. We don't have those anymore. So now when you go out and buy a lighter, you hit a button on it and you hear a real sharp click, pop, and it generates a spark, and then that spark ignites the gas. What you're playing around with is a piezoelectric device. So piezo is a term we use for pressure. Piezoelectric means it generates an electrical signal relative to pressure. The problem is, though, it's got to be a change in pressure. So we don't use these things to measure pressure, but we can use them to measure a change in pressure. Because if the pressure is constant, then the piezoelectric crystal would not put out anything. So those are piezoelectric. So piezoelectric converts a changing pressure into an electrical equivalent. And it can put out some pretty high voltage. So that's what you're doing if you go out and buy a lighter now. And just about everybody's got one. My wife likes candles. So she likes to light a bunch of candles. So she buys one of those lighters that's got the big old long thing on there. And you come up, you hit a button, it snaps. What it's doing is it's coming here and bopping that piezoelectric crystal in there. When you bop it real hard, what does it do? It generates a voltage. Pretty high voltage, too. Probably, I don't know, maybe 20,000 volts or more. And then what does that do? That arcs across the gas, and then what does it do to the gas? It ignites the gas. So piezoelectric, what does it do for us? Well, it converts a changing pressure into an electrical signal. So we don't use these things a lot to measure pressure. We use them to measure a change in pressure. Yes. Well, not on your lighter. Your lighter is digital because it's doing what? It's bopping it real hard and it only arcs once. But even though you keep that trigger down, it don't keep arcing. Right? You understand that? So it's got a little lever in there that snaps, and it pops it real hard and then generates the arc. So we got gas sensors, which is not covered in this lecture. All the gas does is just basically do the same thing. It tries to send electricity through the gas. So we have air. Air is a real good insulator. Gases are basically, most gases are conductive, right? You understand that. So most your gas sensors, that's all they do is they have an electrode in there and they measure the current flow through the electrode and they can measure the amount of gas. So that's pretty much what there's though is that they're not linear. This PTC, a PTC has basically a different curve. These are the ones that's used most often, so these are the ones that we'll look at on the test. So it's non-linear, but the problem is if I'm in my house is going to run on a very narrow band, and that's pretty dang linear between that very narrow band, right? You understand? But thermistors are not extremely accurate, but they're accurate enough. So if I've got a thermistor that's sensing the temperature of a motor, we can make sure it trips at a certain temperature, right? You understand? So it could be exactly accurate. So a lot of your motors have thermistors in them. So if you got a single phase motor, a low horsepower single phase motor, like you got a lot of those in your house, those guys have thermistors in them. But they're thermistor switches. So what they do is they switch when they get up to a certain voltage, right? You understand that? Thermistor is very, very popular. These are photoresistors. This is up in chapter 15. So what does a photoresistor do? Photoresistor. So it changes its resistance with what? Light. Yeah, it changes its resistance in light. These are always, I've never seen one that's positive. These are the different symbols. So anytime you see a symbol that's got arrows coming into it, that means these guys here detect light. By the way, this is the ISO, the international symbol for a resistor, which gets kind of confusing. So this is normally sensors we put inside circles. You'll see a lot of people leave those off. So these guys here vary their resistance with what? Light. These guys are used all over the place. When I was young and they started putting lights in parking lots, they ran off timers. Now, what's the problem with timers? Well, the amount of light we have changes during the season. So you'd be going by a grocery store, and in the summer it'd be 5 o'clock. The lights would be on because somebody hadn't gone in and done what? Changed the timer. We don't have that anymore because why? We got devices. These photoresistors. Most people call these photocells, by the way. So that's a commercial term, photocells. These guys vary their resistance with light. So now I've got a sensor that I could take into an electronic circuit that switches my lights on when it's what? When it's night, and turns the lights off when it, did I say that right? Turns the lights on when it's dark and turns the lights off when it's light. Now I don't have to worry about them anymore. So all these street lights up and down Bessemer Superhighway has what in it? They have these photoresistors. If you ever got one, you would see there's a guy that got a unit on top, and you can see these things as plain as day. And they're usually replaceable. We don't usually replace this guy. Usually, if you replace those, you replace the whole module, but it just pops in there. Pretty neat. Photoresistors. Everybody okay there? Wheatstone Bridge, we looked at that. Photovoltaic cell. Most people call these things solar cells. So the technical name, photovoltaic, right? You understand? So it says, okay, these things generate a voltage with what? From light. It absorbs the energy of the light and transforms it into a voltage. There's a symbol for a solar cell. So we don't get much voltage out of them, but if we hook voltage sources in series, then their voltage adds, right? You understand. If you hook them in parallel, then they're what? Then their current adds. So that's what these big old solar arrays, we don't call these solar cells. These are technically called solar cells. Solar arrays. So what do? Well, they hook some of the cells in series to get the voltage out they need, and then they hook the rest of. Then they hook those in parallel to get the current they need. I think Harbor Freight sells one that's like a 45 watt, and it comes with a lot of stuff with it. This is Hall effect, and those are just magnets. So this is basically a Hall effect sensor. Got to have at least 3 wires. We got to have one for what? Power. We got to have one for ground, and then we have one for signal. And this is usually true for all solid state sensors. Ultrasonic sensors, they can detect distance. They can detect. Well, these are kind of the same thing. They can check levels but they're still checking what? Distance. They can check speed. So they check it one time. Basically, they call them radar guns. These are nothing but ultrasonic. So radar is ultrasonics, right? You understand that. So what do? They send out a pulse, calculate how long it gets back. They send another pulse out, see how long it takes to get back. The distance that you covered in that thing would be what? Would tell you the speed that you're going. We have an ultrasonic sensor over on the control line. I hope that we don't bother Mr. Sanders over there. He's teaching a class. Well, what it's doing is sending out pulses, but the distance can change during the time. So what would happen is it would give us an output if the distance was changing, right? You understand? If it's a digital sensor, a digital ultrasonic sensor will only look for a distance. It won't look for a change in distance. It'll just look for a distance, right? Understand? We don't use that, but it would be kind of like so now on our car. In the old days, all we had was a gas gauge on there. Now we have a light that comes on that tells us when our what? Fuel is low. So you're combining 2 sensors there. You have an analog sensor that gives you the actual amount. It's usually a rheostat, by the way, or it's a potentiometer. And then we have a analog to digital converter that says, okay, if the output of that pot gets down below this voltage, it means you're low on fuel. So most of these sensors are analog sensors, but a lot of our control is done digitally. We either turn something on or we turn something off, right? You understand? So these guys here, a digital ultrasonic sensor, the A to D converter would be built into it. And it can be easily done because it's electronic anyway, right? So we have to apply power to it. The one we have over on the Amatrol line gives us the ability to set what we call a span, which is 2 digital reference points. So what we do is we put those blocks through there. If the block is not the right size, it's going to reject it. This right here would be analog. So this is an ultrasonic detector. I don't know if some of y'all have had ultrasound. It's very popular in for pregnancies to see, check the baby out. But that's analog. I had it done on my legs when I was in the hospital because I laid up so long. They constantly checked me for blood clots in my leg because I was laying on my back so long, and it's basically just the same thing. So these things are constantly sending out waves, and then they when it bounces off stuff, they use that to generate an image of what's there, which is really, really neat. And those are nothing but ultrasonic sensors. And it's becoming popular to put these things all over your car. You see those little circles that split in the center? Those are ultrasonic detectors. One side's the transmitter, one side's the sensor. So now we got cars that can automatically apply brakes because the ultrasonic sensor is constantly looking at distance. Like I said, my wife's van, when she backs up, if she gets too close to something, it's going to start beeping at her. When she's driving along and if a car comes up and gets into the blind spot on her mirrors, it comes up and lets her know something's over there. Piezo-resistive sensors, pressure sensors. These are pressure sensors. And then we got into chapter 15. Everybody okay on light-emitting diodes? So we know what a diode does. What does a diode do? It only lets current flow in one direction. So LEDs only let current flow in one direction. That's Nancy texting me. Nancy's got walking pneumonia, so she won't be into Wednesday. So I texted her this morning and asked her how she was doing, so she texted me and says she's doing all right. So light-emitting diodes. So what's the symbol for a light-emitting diode? Well, it's a little different. So we have the symbol for a diode. Now the true symbol is we're supposed to put this thing in a circle and then draw arrows coming into it. But very seldom will you see that. Most of the time what they do is they'll put the diode and they'll put the arrows light emitting, not light. So it's going to emit light. Which direction is it going to point? The arrows are going to point out, yeah. So these guys, when those electron and holes combine at the junction, what they do is they emit photons, but the energy level for regular silicon is so low, they don't do a lot of photons, and they're at a wavelength you couldn't see anyway. So to turn these on, we have to forward bias them. So what does that mean we got to do? So before they come on, first of all, before they conduct, you have to exceed something called the VF. We call that the forward voltage drop. Everybody understand that? So if you're below the forward voltage drop of an LED, it don't come on. Everybody understand that? Everybody okay? Now, to produce light, they don't use silicon. They use gallium as their base or their substrate, and then they dope it with other things to get the different colors that they need. So how do we make it come on? Well, we come over here, and we have to make the cathode negative in respect to the anode. So if I put it on a test, the cathode has to be negative and the anode has to be positive. Is that going to be true or false? Huh? It's going to be false. Because it's a difference in, or the anode has to be positive in respect to the cathode. But it's got to exceed the what? It's got to exceed the VF. Now the VF of LEDs are higher than the VF of silicon diodes. In the old days, your meter would not measure this VF, but your new meters will. So odds are, if you got a fairly new meter, you will be able to measure the VF of an LED. Which camera do I have up? Okay, I got this one. Okay. So here's a light emitting diode. By the way, the lens does not determine the color. The lens enhances the color that the LED produces. And I'm going to come over here and put this in. Now, on these are standard LEDs. What you can tell is the short lead. So notice when it's new, you have a long lead and a short lead. The short lead is the cathode. Now the problem is that I clip this thing off, then I've lost that indicator. So another thing they do, I don't know if it'll show up on this camera or not, but when you look at it, you'll notice that one side of the bottom of the lens, it's got a little lip across the bottom. Well, one side is flat. Well, the flat side is the cathode. Now, why they do that in two different ways, of course, is to, when you cut these leads off. So you know you're going to cut these leads off when you solder it in, right? But the other way that we can do it is we can check these things with a newer meter. By the way, these bigger LEDs, they won't turn on. The meter don't put out enough current, so they don't turn on, but the some of your small LEDs are small enough to turn it on. So I've got my meter on the diode scale, and I'm going to come over here and I'm going to put the red lead on the cathode. I'm going to put the red lead on the anode and the black lead on the cathode. As soon as I find my meter, guys. So this is the anode, this is the cathode, and it's measuring about 1.7 volts. So silicon is around 7/10. Gallium doped is different depending on the color. And let's see, nope, this LED doesn't come on. But I can take this little old tiny one right here. So here's the cathode. It's a short one. Double check it with the flat side. And then I'll put this in here. Now, odds are this meter will turn this guy here on. We'll see. See it? A forward bias, reverse bias. Forward bias, so this is red. This has a VF of about 1.6 volts. See, so they're not the same. But notice this guy, can you see it actually come on? But don't expect that all the time. It depends on the size of the LED. So I can check this one, and you won't see it come on. Oh, yeah, it does, too. Barely. Can y'all see it? So this is the VF of the diode. We check it the same way, but it's going to be a lot greater than 7/10 of a volt because it is not silicon. So what we're trying to do is get a semiconductor that we can dope, and we take a lot of energy to cause those things to combine. They develop more photons, and now they're visible. By the way, you got to be real careful with these things. The VF of an LED is very low, usually around the order of 6 volts. If you exceed the VF of an LED, the VRRM, the reverse breakover voltage, right, or what we call the PIV. If you exceed the PIV on a regular diode, you are going to mess it up. Now we do that on a Zener, but we protect it with a resistor, right? You understand? So usually if you got the data sheets, if you don't know it, then we assume it's right around 6 volts. And if you exceed the PIV rating of the LED, you will bop it, right? Y'all understand that? So we don't use these things by themselves. We have several methods that I can use if I'm going to put this thing on high voltage. One thing we can do is we can come over here and put a standard diode in series with it, and then put our LED right here. And then we'll put a resistor. So this right here would be the LED. This might be a 1N4001, which has a breakover around 50 volts. But we see this a lot. So this guy right here, but now when you we're going to deal with well, this guy here would be about 0.7. This guy right here would be about 2 volts. So you're dealing with almost 3 volts drop. If you're going to run these things in an AC circuit, then normally what they do is we have a pretty good sized resistor. I'll come up here and show you how to do that in a minute. Then I would come over here and I would put my LED like this. And then I would come over here and I would put a regular diode opposite like this. So now I can run this thing on AC. So when this goes positive and this goes negative, then it's going to bypass this, right? You understand that? When this is positive over here and this is negative, then the current would flow through the LED. The important thing is sizing that resistor right there. So you can run an LED on just about any voltage above VF, but you're going to have a what? You're going to have a resistor, and you calculate that resistor about the same way that you calculate. It's a little easier though than you would be for a. So we'll try to look at a data sheet. So this would be in a DC circuit. This right here would be in a what? An AC circuit. So yeah, we got TVs. The LED comes on. We got all kind. Of course, the LEDs. That's not really TVs. It's already in DC. But you'll see a lot of AC devices that's got a little LED on it. Perfect example. No, this is a neon bulb. But a lot of your surge protectors. I bought a voltage converter and carried it to Germany with me, so I could switch it so it divided by 2. So they're 230 over there. I could divide that by 2. It had LEDs all over it, and it didn't have any real electronics in it, but it was no big deal because wow, they just hooked up this circuit right here and just chose the right resistor. So how would you choose the resistor? Oops. Well, you look at a data sheet, right? You understand. And then your data sheet would tell you the current. So this guy right here says, okay, I want to do what? 50 milliamps. Now, normally we don't run it at its maximum current. That's maximum current. Normally we run it at about half that because, and then this would be the VF. So this is right here. This is what we want. 200 milliamps. So that's my current, right? You understand. So let's say I got 120 volts DC over here, and I want to run this LED. Well, first of all, I'm going to put a resistor, right? You understand. Well, what size resistor? Well, if this is 120 volts, this guy here is going to drop 1.5 volts. What would I need that resistor to drop? Huh? Yeah, 118.5 at what current? At 20 milliamps. R is equal to V over high, 118.5 divided by 20 milliamps. There's my resistor, and you would round this up. If it fell right on the value, that's what you'd use. If it don't fall on the value, you would round up. You would go to the next higher value, right? Does that make sense? It's not going to hurt to run it at a little less current, but it will hurt it to run it at too much. So what size resistor would I use there, guys? For this LED. What's that? 5.9K. And if that's not a standard value, then what would you do? You would round up to the next higher value. So yeah, you can run these things at almost any voltage. Are we okay? But this is a chart that shows you the different colors, and the VF varies with the current, the colors, and the current varies with the colors. How do they get different colors? Well, they take gallium and they dope it with something else. So notice every one of these starts with what? Gallium. So that's what we make LEDs out. And then they dope it with different materials to get the color they want. Originally, we had very, very few. By the way, the guy that created the white LED, so that's an LED that's got to emit at least 3 colors, right? You understand that? He won the Nobel Prize for Physics. Thank goodness. So years we did not have white LEDs. They worked on it. They got blue, and we can still see them out there. Your cheaper flashlights just as a real light blue. But now we have true white LEDs. Thank goodness. These guys use, these displays use liquid crystal displays. They have to be backlit. For years, they were backlit by fluorescent tubes. So you look at some of our monitors, they're real what? They're real thick. Why? Because they got a fluorescent tube behind them. You look at these monitors, though, see how thin they are? Why? Because these are backlit by LEDs. But these are still liquid crystal, by the way. It's just that they're backlit by what? By white LEDs. So now we go out, we buy these cell phones and stuff, we can get them super thin, even though they use liquid crystal displays. They're backlit by LEDs. Somewhere I should have figured out where's that. Symbol for LED. We got LEDs all over the place. These are referred to as 7-segment LEDs. We can display any number on that. We have these signs that scroll all the time. These are nothing but LEDs. We have these big old jumbotrons or these big old displays. These are nothing but LEDs. Are we okay? If you don't know, normally use 3 volts or 50 milliamps if you don't have a data sheet. But that's, if you do have the data sheet, then you look it up. This shows you how to data sheet. Normally 2 volts at 15 milliamps should be okay. So if you don't have the data sheet, if you got the data sheet, if you know the part number, you look it up, right? You understand. Problem is that they don't usually put part numbers on them. The arrays, they'll put part numbers on them, but the LEDs themselves, they don't. 7-segment displays, we have 2 types. We have what we call common cathode and common anode. So common anode, what we would do is we would put power on pins 3 or 8. Now, normally these things are set. You don't have to put power on both those pins. These guys are usually placed on printed circuit boards, and since they have pins available, they put power coming out on both sides, so you can power it on either side. And that way it may be easier to power. And y'all see common anode. So common anode, all the anodes are connected together. So we'll turn these things off on with a lower voltage, right? You understand that. And then a common cathode, we would come up here and connect this to common, and then we would turn this on with power. Why they called it a 7-segment display? Because we have 7 segments, not including the decimal point. By the way, this has been this way as long as I've been around. These segments are given names. So you just start at the top, away from the decimal point, and this segment at the top would be called what? A, then you just go around, B, C, D, E, F, G. And what we do is we turn on different LEDs. So different pins have different LEDs. This is a common cathode LED. So what I have, this is minus. This is my minus power supply. I can't connect. I'm using 5 volts. The VF on these things is roughly 2 volts, right? You understand. So I cannot hook power directly across the LED because it will do what? It will burn it up. We used to put LEDs in the DC trainer. They have one little lab they do DC. What do them knuckleheads do? Well, they get them things on. They look like lights. They'd put them in the power supply, start cranking the voltage up. It didn't work. They'd spin them around. They was blowing those LEDs left and right because they put them across power. We don't put it across power. We got to have at least one resistor. So this is pin. This power is not quite like the one in the book, but either pin 3 or pin 8 is ground or common. And then I come up here and I jump to the segments. So notice if I come up here and jump, what segment is that? Here's the decimal point. So what segment is that? Well, that's the V segment, right? You understand that? So I'll move it over. That right there would be the what? The A segment. I'm not going to put it right there. That's power. This right here would be the what? This would be the F segment. Put it right there. That would be the G segment. Go down here. That would be the E segment, right? D, right? Okay. Got to be real careful on this because if I touch right there, I got a short circuit. C. So what I can do, if I want to make this thing display something, then I would do a lot of jumping, right? So let's say I wanted to do the number 3. So what segments do I need to turn on? You remember where A was? Well, let's find it. I don't remember. So I would have to put a power right here. Oops, don't want that one. Want that one. Okay. Put power right there. Oops, don't want that one. Want that one. We got the pin out on this thing, by the way. By the way, I'll show y'all in a minute. So I'm going to be real careful. I need the A segment. Anybody remember where the A segment was? It was across the top somewhere, wasn't it? And there's the number what? 3. By the way, notice that I got one resistor. Every time I hook up a segment, the current flow for that segment flows to that resistor, which makes the voltage drop on this go up, which means the voltage available to this goes down. So notice as I hook up segments, every one of them get what? Get dimmer. So normally we don't use one resistor. Normally what we would do is we would put a resistor on each segment. So this is the one that we got right here. So normally what I would do is I would come over here and I would take like pin 8 and then I would hook it up. I'm not going to put the arrows. And then what we would do is we'd put a resistor in each leg. And then I would come over here and I would put, oops, sorry, wrong one. Ours is a common cathode, not a common anode, Rich. So the cathodes are pointing up. So normally this is what you would do. So that way each one's got their own resistor. 5 volts, that's usually going to be a 470 or a 330. So you'll see a bunch of these. These are not very low, 15, 20 milliamps is not a lot of current. So that means we don't have to use. So if this is 5 volts, this guy drops 2 volts. Oops. So if this is 5 volts, so if I'm putting, if this is, of course, this would be common, right? And then I put a resistor over here, and I put plus 5 volts. If we take for granted that this drops around 2 volts, that means that resistor would have to drop 3, right? No, so R would be equal to 3 divided by 15 milliamps as rule of thumb. What size would the resistor be? Huh? Yeah, the standard is around 330 ohms. Now, what would be the wattage rating? Okay, so now I'm using 3 volts squared divided by 330, V squared over R. So what would be the wattage rating on that? What's that? 30 milliwatts. A quarter watt resistor is 125. So these resistors can be really, really, really small, right? You understand? So what they'll do most of the time is they'll build these on a single wafer, and we call these resistor packs, by the way. And there's usually, so this is a 1, 2, 3, 4, 5, 6, 7, 8. It's usually 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And then they'll put this in a single package. So you'll run into a bunch of these. And I didn't draw it out. This actually would come down through here. Now, when you do the pins on these things, I'm going to pass this around. So what I've got is I got what they call a resistor pack. It's got a little notch in it. One, two, three. I'm sorry, my display's moving. 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. These guys here are numbered. They're numbered 1, 2, 3, 4, 5, 6, 7, 8. And then what we do is we come straight over. This would be 9, 10, 11, 12, 13, 14, 15, 16. So we have a resistor between pins 1 and 16. So you'll see a bunch of these because the power is so low that we can integrate these. So this is the resistor pack. The way this thing works, it's got 331, so it's kind of a color code, but it's not. So if this was color coded, it would be brown, 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 right? I'm sorry, it'd be It'd be orange, orange, brown. Okay, so that would be 3, 3, and 1, 0. So this is another way they use where they don't give the color, they give the numbers. So this is 3, 3, 1. So what would that mean? 3, 3, and 1, 0. So that's a very common way of doing these resistor packs. But if I was to come up here and use it, I'd have to put it across the box. There would be a resistor between here and here. I don't know if I can get my meter on there. Put it on ohms. It's supposed to be 330 ohms. And I would measure between this pin and this pin, and it measures 330. Woo. So there's a resistor between each one of these. So normally when you get into these 7-segment displays, they're not going to use a lot of individual resistors. They'll use what? We call these things what? Here you go, Mitchell. These are called resistor packs. This is called a DIP, by the way, which is a dual inline package. A lot of times they'll put them in what we call a SIP, which is a single inline package. And normally a SIP will have the common already set up for you. 7-segment displays. You ever seen these guys? These guys are all over the place. Odds are there's a lot of things that don't display characters, like your cable box you got at your house is nothing but probably LEDs, right? What we do on to display using LEDs, we set up what they refer to as a triad. Y'all know what a triad means? Threes. And the 3 prime colors that they use, well, they actually use 4. They use red, green, and blue. And usually they're all set from each other. They don't have to be. These LCD screens, they're set up like this. So when we look at these, I'm gonna let y'all see them. They're set up in little stripes. What would be the 4th color? Black. Good. Yeah, so these are mounted in a black background. And now we can do just about every color there is that the human eye can discern. Sony came out with one where they added a yellow, by the way. Y'all remember that guy? You couldn't tell the difference. Unless you had 2 side by side, which is pretty interesting. Oops. Got a monitor up and I don't know what this just let y'all look around this thing. Of course, white, what you're going to see is all of them's turned on. When you get over here, you'll see nothing but blues turned on. No, this is not quite blue. This is a blue-green. White, you'll see all of them turned on. Yeah, come on, take a look. Yeah, let y'all take a break. Now these are liquid crystals, but they work on the same feature. Yeah, I said it's flat. So that's a bluish green, ain't it? See there? But the red's turned off. You get on white, all three of them's turned on. And what does our eyes do? We blend those together and create colors.